In 1955, an Air Force engineer named Clark Beck created a new material for NASA that would permanently transform the future of space travel. The invention was a thin foil film capable of reflecting 95% of radiant heat. The concept sounded simple, yet the impact was enormous. Without that breakthrough, many milestones in space exploration could never have happened. The material became part of spacesuits, lunar landing equipment, the space station, and even the James Webb Telescope. Years later, once the technology entered public use, people discovered that it could also serve as a highly effective way to reduce unwanted heat inside residential buildings. Today, that system is known as a radiant barrier. The cost can be as low as 10 cents per square foot, yet studies have shown it can lower attic temperatures by 30 degrees Fahrenheit, while reducing household cooling expenses by as much as 17%. Even so, despite being among the least expensive and simplest upgrades for lowering heat gain, fewer than 10% of existing homes across the United States currently use radiant barriers. To understand why this technology matters, it is important to first understand how heat enters a house. Heat moves in three separate ways. The first method is conduction. This happens when heat travels through solid materials through direct contact. As the outer shell of a home becomes hotter, that warmth slowly transfers inward into the living space. Depending on the structure, insulation, and construction materials, conduction usually accounts for around 10 to 30% of the total heat movement inside a home. The second method is convection. This is heat transported by moving air through drafts and airflow. It can enter through gaps around doors, windows, or rim joints. The exact amount changes from house to house, but convection generally represents roughly 15 to 30% of heat gain or heat loss. In older drafty homes, the figure can climb close to 40%. Then comes radiation, the largest contributor of all. Radiant heat travels through electromagnetic waves, similar to the warmth felt from sunlight on human skin. This form of transfer can create anywhere from 40 to more than 65% of a building's heat gain. Windows are an obvious source because they allow not only visible light to enter, but heat as well. Yet beyond the windows, the attic becomes the largest source of unwanted summer heat inside most homes. Imagine a bright afternoon in July. As sunlight strikes a dark shingle roof, the roofing surface absorbs huge amounts of energy. The underside of the roof deck effectively turns into a massive radiator hanging directly above the ceiling. That creates several serious problems. If HVAC ductwork passes through the attic, the additional heat can increase system load by 22%. Energy bills rise, and the cooling equipment experiences extra strain. Meanwhile, the roof continues sending radiant heat downward. Since air absorbs very little radiant energy, the heat moves across the attic until it hits a solid surface. In most homes, that surface is the insulation spread across the attic floor. The insulation absorbs the heat, warms up, and then gradually conducts that energy into the rooms below. Architects and engineers have understood this issue for many decades. Primitive forms of radiant barriers have existed since at least the beginning of the 20th century. The earliest reflective foils designed for buildings were patented in Germany and the United States during the 1920s and 1930s. By the 1940s and 1950s, companies including Infra Insulation were already marketing foil insulation products to homeowners across America. Early reflective insulation products attracted some attention, but most homeowners never fully understood how radiant heat actually worked. Because of that, the technology failed to spread on a large scale. Everything changed during the middle of the 1950s. As the space race intensified across the United States, a young United States Air Force engineer named Clark Beck received a difficult assignment. He needed to stop spacecraft from destroying themselves during atmospheric re-entry, when the craft skipped across the upper atmosphere in a phenomenon he described as red-hot wings. The challenge pushed him deeper into radiant barrier research. Eventually, NASA created a method that sprayed vaporized aluminum in a thin layer onto plastic film sheets. The material felt similar to cellophane, yet behaved like polished metal when exposed to heat. More than 95% of incoming radiant energy could be reflected away, even though the material weighed only 17 pounds for every 1,000 square feet. The breakthrough solved multiple problems at once. Beyond Earth's atmosphere, air does not exist. That means radiant transfer becomes the only natural form of heat movement. Temperatures in space can also shift violently within moments. An astronaut's suit or spacecraft may face temperatures exceeding 500 degrees while exposed to sunlight, then plunge to more than 400 degrees below zero once in shadow only seconds later. Using traditional insulation to survive those conditions would have required a suit nearly 7 feet thick to provide the same level of protection. For a period of time, this reflective film remained limited to aerospace applications. Later, it entered the public domain. Then, the oil crisis of '73 drove energy costs sharply upward, creating demand for affordable ways to lower household expenses. Radiant barriers quickly found their way into residential construction as a practical energy-saving solution. The reason a thin foil layer can shield astronauts in space or lower attic temperatures by as much as 30 degrees Fahrenheit comes from the combined relationship between reflectivity and emissivity. Reflectivity measures how effectively a surface bounces radiant heat away. Emissivity describes how efficiently that same surface releases absorbed radiant energy back outward. For every solid material, those two properties always combine to equal one. A black asphalt roof shingle, for example, reflects only around 10% of radiant heat, while re-radiating the remaining 90%. Clean aluminum foil behaves almost the opposite way. It reflects approximately 95 to 97%, while absorbing only 3 to 5%. But every radiant barrier has one critical engineering requirement. There must be nearby airspace. Radiant heat can only be interrupted by a reflective surface when the surface faces either a vacuum or a gas, which in this situation is air. If foil becomes trapped tightly between solid materials like gypsum board or plywood, heat simply bypasses the reflective layer through conduction. That is why radiant barriers require at least one exposed side facing open attic space, or an air gap measuring a minimum of 1 inch. Once the science becomes clear, the system itself is remarkably simple, yet the results can be substantial. Oak Ridge National Laboratory tested several radiant barrier methods inside a climate simulation chamber heated to 140 degrees. Their findings showed that radiant barriers stapled beneath rafters reduced heat flow by nearly 50%. Foil placed directly on attic floors lowered heat transfer by 1/3. Liquid reflective coatings sprayed across attic floors reduced it by 19%. Outside laboratory conditions, the performance continued to show real benefits. A monitored project involving 8 upgraded homes in Central Florida found that radiant barriers reduced cooling energy consumption by an average of 9%. Peak cooling demand, the period that places the heaviest strain on air conditioning systems, dropped by roughly 16%. For a house measuring between 1,000 and 2,000 square feet, the savings translated to roughly $13 to $27 removed from the monthly utility bill. At first glance, that may not appear dramatic, but considering the installation can be completed personally over a single weekend for only a few $100s, while continuing to perform year after year, the payoff becomes difficult to ignore. The effectiveness of radiant barriers is already clear. However, before installing one, there are several important limitations and conditions to understand. Not every home receives the same level of benefit. Climate plays a major role. In regions with long hot summers, radiant barriers perform extremely well. In colder climates, though, the reflective surface can also push away useful solar heat during winter months, heat that may otherwise help warm the building naturally. Another important point is that attic radiant barriers are far better at blocking heat from entering a home than trapping warmth inside it. That happens because winter heat loss from houses mainly escapes through convection rather than radiant transfer. Still, there's one location inside cold climate homes where radiant barriers remain highly effective, not above the ceiling, but beneath the floor. Research modeling has shown that barriers installed under floors can reduce total floor heat loss by nearly 95%. Long-term performance is another factor worth remembering. The system requires almost no maintenance, but dust creates a serious problem. When foil is laid flat over attic insulation, ordinary household dust gradually collects across the surface. Over time, the shiny material turns dull gray and begins absorbing heat instead of reflecting it. One study discovered that reflectivity could decrease by a factor of 10 within only 2 years. In many cases, the dust causing the damage is barely visible. That is one major reason. Experienced installers prefer attaching radiant barriers vertically along rafters instead of placing them flat across attic floors. There are also a few smaller concerns to consider. If HVAC ducts are not located in the attic, the overall benefit becomes smaller because protecting duct airflow from heat is one of the barrier's greatest advantages. In addition, aluminum conducts both electricity and radio signals. A continuous metallic layer across the roof may slightly weaken cellular or Wi-Fi reception. In most homes, this is unlikely to create noticeable problems unless signal quality is already poor. At this point, the operating principle behind radiant barriers is clear, along with the situations where they deliver the greatest value. The next step is understanding installation methods. For newly built homes or complete re-roofing projects, foil-faced sheathing, commonly called radiant barrier OSB, is usually considered the best option. The reflective layer and structural panel are installed together in a single step with almost no additional labor required. With high-quality panels, solar radiation reflection can reach as high as 97%. For existing attics, the most proven retrofit method is known as staple-up installation. This process uses reflective foil stapled beneath roof rafters while leaving enough airspace for proper reflective performance. Material costs generally range from 10 to 50 cents per square foot, placing a typical installation at only a few $100s plus a weekend of labor. Anyone installing the system personally should use perforated foil instead of solid foil. that allows moisture to pass through safely rather than trapping humidity and turning the attic into an environment where mold can develop. Ventilation openings must also remain clear at all times. Soffit vents, ridge vents, and gable vents should never be blocked. Closing those pathways disrupts the home's natural stack ventilation system and can actually increase attic heat instead of lowering it. The radiant barrier itself is simply a sheet of metallized film. It originated from the challenge of protecting astronauts in space. Its entire function depends on one simple principle. A reflective surface cannot absorb the energy it sends away. And the largest source of summer heat entering a home does not arrive through direct contact or moving drafts. It arrives as invisible radiant energy, something traditional insulation was never originally designed to stop. If you found this breakdown useful, share it with others interested in energy-saving technology and practical, self-sufficient living solutions. More innovations like this continue to change how modern homes handle heat, efficiency, and long-term energy costs. Thanks for watching. See you in the next one.